Okay, so we're going to look at a simulation that I created today in order to look at how the central limit theorem works. Now, when we talk about the central limit theorem, we talk about this idea that when we take a sample and we measure a statistic about that sample, say the mean, then what we end up with is an estimate of the mean of the population. And the sample varies a little bit from the mean of the population. But we talk about how as the sample size grows, the variability around that mean changes. It gets smaller as the sample size gets larger. And when we think about this, we think about taking repeated samples over and over again, and then seeing how that distribution falls out. But in reality, we never really take multiple samples over and over again. Instead, what we do is we take one sample and we use our knowledge about how repeated samples would behave. But sometimes it can be helpful to just look at like what would really happen if we took repeated samples over and over again. And so I've created this simulation in Excel to sort of illustrate an example of what would happen if we were to take repeated samples. So I'm using SAT scores as our example. SAT scores have a mean of 500 and a standard deviation of about 100 for each subject test. And again, this is a rough approximation. This is the goal at any rate. And what I've done is I've created the simulation. Now this takes a while to set up, so I didn't record the setup, but I want to show you exactly how the simulation is created in case you want to create one of your own. So let's look at one of these SAT score values. Now the heart of the simulation is this random number generator, RAND. The RAND function produces a number between 0 and 1, and it's randomly generated. It's a pseudo-random number, of course. But we can think of this as the percentile test score for our simulated SAT score. So if I were to take a randomly person out on the street who takes the SAT, and I were to record their number, then this is supposed to simulate sort of where in that percentile range they fall. And in order to then convert that percentile value from the RAND function to the SAT score itself, we then use the norm inverse function. The RAND becomes that percentile input in the percent part of the norm inverse function, and then we specify the mean and the standard deviation. Now, percentiles generally are going to export sort of decimal place values, and when you take the SAT, you don't get decimal place values. You don't even get values that have like the final digit. They're just all rounded to the nearest 10 points. And so the round function around this then is rounding this to the tens digit. So normally you count digits past the decimal place. So 0 would round to the whole number, and 1 would round to 1 decimal place, and 2 would round to 2 decimal places. But if you want to round to the tens digit, then you use -1 because it's 1 digit in front of where the whole number would be. And so these are our simulated SAT scores. And every one of these formulas is basically constructed the same way. I just wrote the formula one time and then copied it down to get a sample size of 10. And then I copied the mean. So we have an average of these 10 values. And you can see the average for our first sample is around 500. It's not exactly 500, which I would never expect to really see, but it is close. And then I calculated the standard deviation on our simulated sample. And then what I did was I created a bunch of these samples. So here is one sample of size 10, and then I moved the function over, I copied and pasted, and I created another sample of size 10. And you can see slightly different mean, slightly different standard deviation, but they're both sort of on either side of what the distribution says they should be, which is 100. And so again, I made actually 55 of these 10 sample examples. So I copied and pasted my 10 sample calculations all the way down. And again, you can see if you look at the means, they're all around 500. The standard deviations are all hovering around 100, some a little higher, some a little lower. And then what I did after I'd calculated my 55 samples of sample size 10, then I averaged all the means together. And again, you can see this got closer to 500 than most of the means in our individual sample size 10 samples. And then I calculated the standard deviation of those means. And this is where the central limit theorem comes into play. The central limit theorem predicts that the distribution of these means is not going to have a standard deviation of 100, which is what the individual observations have, and what the standard deviation of each individual sample has. But if you're calculating the standard deviation of these means, what you're expecting is to get the standard deviation divided by the square root of n. So we have 55 samples here, and our original standard deviation was 100. So we could calculate 100 divided by the square root of 55 and get an estimate of what we would expect the standard deviation of these means of these sample size 10s would be. This would be square root of 10 because it's each sample is a sample size of 10. And if we do that calculation, we get 31. Now notice our 31 that we calculated is very close to the 29 that we got from our samples. So again, this is an indication that we're estimating using estimates, but our expectation is that we should get a standard deviation of these mean samples to be around 31, and we're getting a value for, again, the standard deviation of these means to be in that same ballpark. Now, you may have noticed when I calculated this formula, all of my samples updated. This is what happens when you do random simulations in Excel. If you use a random number function, every time you calculate something, it will recalculate all of your samples, which can be very useful if you want to just like see over and over again more and more simulations of the same quality, the same type. And in fact, if you go to the formulas menu, there's an option here for just recalculating all of the values in your spreadsheet so that you can, again, see what happens as you keep changing these values. So if I do that now, so now my mean of means is not 501 or 503, it's 497. So again, still in that same 500 ballpark. And my standard deviation of my means is a little bit higher than my 31 and not lower than my 31, but still in the same ballpark. So I could try it again. And again, now it's still a little further apart, but I can do this several times. And I can see that I got closer. I'm back to that 29 range. 500, the mean is closer. My standard deviation is a little lower. And again, you can see everything kind of stays, the standard deviations of those means in the 27, 28 to 30, 31, 32 range, 34 in this case. And my mean of my means is all staying, again, in that ballpark of 500, give or take. And I put all of my data, my mean data, into a histogram. And as we go ahead and we keep calculating, the histogram will update as the values of my means change. But you can see it's kind of normally distributed, which is what you would expect in most cases because the data is originally normally distributed. But because the sample size is relatively small, you do get the possibility for greater variation. So here my mean is higher, but my standard deviation is closer to expected. So this formula that we're, again, this is an expectation that we're having. If we were to do this over and over again and average our standard deviations, we would expect to get around 31. When we actually do the samples, we don't always get exactly that because of the randomness. Now, I repeated this exercise for sample sizes of different values. So after doing sample size 10, I created using the same formula. Here's our same formula to create some new simulated data, but now I'm doing sample size 50. And then at the bottom of my sample size 50, I'm calculating the means and the standard deviations. And again, we can see the means are all pretty close to 500 and the standard deviations are all pretty close to 100. And they're a little closer than they were before because our sample sizes are bigger and there's less variability in the means when we have bigger sample sizes. And then I copied them all out until I had, again, 55 samples of size 50. And then I calculated the mean of those means. So I got really close, and the mean of the standard deviation, the standard deviation of those means. So again, I took this row of data and calculated the standard deviation. Now notice that it went down. The sample size of 50 has less variability in the mean than the sample size of 10. And again, we can, if we want to, calculate our original standard deviation divided by the square root of 50, which is the size of our individual samples, and see what we expect that variability around that mean to be. And so we're up actually around 14 is our expectation. So again, you can see when I hit enter, it recalculated. I've got a mean of about 500 again. My standard deviation is a little higher than I expect. But if I calculate again, now it's a little lower than I expect, with the mean still around 500. And notice these means of means are, again, closer to the true population value, and my standard deviation is smaller. And again, you can update. I created this histogram based on those mean values. And you can see that as we recalculate, the histogram is going to update as well every time I redo the sample. And sometimes we get very normal looking distributions. They look a little more normal than the examples we had before. But still, occasionally we get weird looking ones. And then I did this one more time. I calculated with sample size 100. And again, this is using our same formula for each of the individual SAT scores. Sample size 100. And then again, I calculated the mean of each of these samples and their corresponding standard deviations. And again, for each individual sample of 100, you can see the means look like they're a little bit closer, typically, to the 500 than previous examples. The standard deviations fall around the 100 range. And when I calculate the mean of means, again, I get a value around 500. Our central limit theorem says that the mean of the sampling distribution should fall around the true population mean, which we know in advance is 500. And our standard deviation has again shrunk. And again, we can check what we expect it to shrink to, which should be 10 in this case, because we're taking our original standard deviation and we're dividing by the sample size, which is the number in each of our individual samples. And we're getting 10 because the square root of 100 is 10. And so again, we can recalculate and we can see from our histogram. This is the histograms sometimes look a little weird because we have only 55 of these samples as opposed to hundreds. But we can see from our calculations The means are very close to 500, and the standard deviations hover in this range right around 9, 10, or 11 in most cases. Now, I wanted to look at then what happens if we have larger and larger sample sizes, and how can we kind of visualize the differences between sample size 10, sample size 50, and sample size 100 in another way, and sort of visualize these changing standard deviations. And so what I did in my next sheet was I copied, so I actually copied a particular stage of the simulation, so that my numbers wouldn't keep constantly updating, so that they're fixed. And I made lots and lots and lots of copies of each of my sample size 10, sample size 50, and sample size 100 for just the means. So we go all the way down, I mean, lots of them. Lots and lots and lots of them, so that we have lots of simulated calculations of our sample means. And so I recorded them and then pasted them as numbers again, so they wouldn't keep updating. So I have a fixed sample to work from. And I did that for each of my individual samples. And what I did then was I calculated the mean of those samples. Again, the mean of the means. So for my sample size 10, for these hundreds of samples, I got 497, I got 500, 499. So they're all, again, around 500. I calculated my standard deviations. These were, again, the standard deviations of these means. Again, I'm getting 32 for the sample size 10, about 14 for the sample size 50, and about 10 for the sample size 100. And for each of these, I then calculated, as I did in the previous page, the expectation from the central limit theorem that this should be about sigma over the square root of n. And that's what we have here. For my sample size 10, it's 100 divided by the square root of 10. For sample size 50, it's 100 divided by the square root of 50. And then for this one, it's 100 divided by the square root of 100. And you can see that the calculated values that we get, again, random noise, they're not going to be completely precise, but they are very similar to what we would expect. And if we were to, again, repeat this or have even more examples, then eventually we would expect to get closer and closer and closer to our expectations. Now, one way I decided to illustrate this is to actually calculate a box plot of each of these values. And you can see the way that our means are spread out in each of these cases. In our sample means, we have some that are extremely low, around 400 as an average, which is very unusual, but we have a lot of them. And some are as high as like 590 or something like that. But then typically the average is going to be much closer to 500. Now, as we calculate a box plot for the next line for the sample size 50, again, the average is going to be around 500, but what we see is that spread of values has shrunk. Again, that's part of the central limit theorem. The bigger the sample size, the less variability in those means. And then similarly, for the sample size 100, it shrinks further. The mean is still at the same place, but the spread of the possible values has been reduced. And then what I've done is I've made histograms of each of these graphs. Now, each of these data sets. Now, what happens when you make a histogram is the graph in Excel will set its axes. They'll all be the same size graph, but they'll reset the axes based on how wide the data set is. And so that's not a great way to compare that spread of the distributions. So what I did was I resized my histograms after I made them so that you could see the spread visually. And to see all of these, I'm going to have to shrink the image just a little bit. Maybe one more. Here we go. So this top graph here is this distribution of sample size 10. And you can see it's super wide, centered around 500, right there in the middle, but it's relatively speaking, very spread out. Sample size 50. So here's 458. So it starts somewhere in the middle of this bar and it ends at 354, which is somewhere in the middle of this bar. But the sample size 50 is not as spread out. It's still normally distributed. This looks much nicer than some of our samples, our 55 samples. But now we've got hundreds of samples. And so the histogram looks very normally distributed, very symmetric. But look how much wider the sample size 10 variability is relative to the sample size 50. We can see that it shrunk. Again, normally Excel will make our graphs exactly the same size. And so then you can just tell by the numbers. But I resized these graphs so that the numbers would line up so that you could more easily visualize the shrinkage. And so this is narrower, less variability than the sample size 10. And likewise, if we look at the sample size 100, this is kind of our normal size graph. 472 falls in this bin right here, and 522 falls in this bin right here. And so again, the variability in our means has been reduced yet again. Every time you increase the sample size for the first sample that you're taking, how many SAT scores are you looking at in this group? That reduces the wiggle room of how far that mean can move around. And so again, this looks, again, very normally distributed with a mean at 500 right here in the middle. And the amount, the spread of that distribution of those means has been, again, reduced again. And we could keep doing this with larger and larger samples, but this is an illustration of how the central limit theorem works. And so when we do these calculations on samples, on confidence intervals and things like that, this is why we use the standard error formula, the sigma over the square root of n, from the central limit theorem, because this is how sample means behave. Now, again, the whole point here is to understand how an individual sample behaves in this wider context, because we are never actually physically going out and repeatedly sampling. Instead, we're taking a single sample and we're using our knowledge of this fact in order to make our estimates.